Okay, welcome back to everyone. So this is our afternoon of the first day, and we continue with Anders and his second talk on structure compressed sensing and imaging.
Okay. Can you hear me well? Is it on? Yeah, it's on. Good. So let me just do a little bit of a recap what we did before lunch, because I want you to have these things fresh in memory. So we'll just go through a couple of slides first. We started by asking, does compressed sensing work? And argued that it seems to work, given that you can go from this to that. The key question is to figure out why, and to be able to understand the way that you can actually get this result here and not that. And I will tell you explicitly what is going on here in about 15 minutes when I've covered the theory. Okay. So we've sort of convinced ourselves that yes, compressed sensing can work in inverse problems. And then I showed you this image, and I claimed that if you understand what is on this image, you understand compressed sensing, which is of course a little bit of an exaggeration, but I'm going to try to make that claim later on when we've gone through the theory. Okay. And what we did was that we went through the very sort of quick 5 minutes course on the classics of compressed sensing, where we were able to distill the pillars. There's the sparsity pillar that you see from here. You need your signal or your vector to have S important coefficients and no further than that. And then it was this incoherence parameter that seemed to be important. And the way that you did the sampling here was completely uniform at random. And we also discussed a little bit about the restricted isometry property and uniform recovery. And these were sort of the old pillars, if you will, of compressed sensing. Now, we went through the flip tests and did conclude that, yes, please. Oh, really? Oh, shit. If I do like this. Whoops. Is it better now? Not really? Hello. Yeah. Oh, that's quite loud. Okay. Is it better now, sir? Should I speak up like this? Okay, I'm going to speak louder. Try that. Okay, so we convinced ourselves that there's some underlying structure here, simply because we did this flip test. And we said, well, if I cannot recover all types of signals, well, there must be something, some kind of structure underlying here, and that's what we're going to try to figure out. And then we covered a little bit of the idea of sparsity. So I claimed that the world is sparse in xlets. And we argued that we could compute the wavelet coefficients of an image and throw large parts of them away and still get a good quality image. And that's sort of the basics for compressed sensing and the idea of sparsity. And then we covered a little bit of the idea of the restricted isometry property, and which I claim does exist if you have random matrices, like random sub-Gaussian matrices, which is great. It's a beautiful theorem. However, if you do sample with random Gaussians, you tend to get French Impressionist images back. And that may not be what you want if you're doing, for example, MRI. However, we did note that the flip test actually works, and you're getting exactly the same quality regardless of what I do with the coefficients. So there is some consistency with the theory, at least. All right. And then we argued that that actually is optimal. This S log n factor is optimal if you would like to get recovery of all vectors. And the interesting thing is that if we take another type of sampling and instead of random Bernoulli, we seem to do better. And that suggests that we should actually do better than this S log n. And I'm going to address this a little later on when we have the theory. OK, so we argued that one of the key problems with the standard theory was that if you actually would use matrices that you would see in practice, namely a combination of, for example, the discrete Fourier transform or the Hadamard transform with wavelets, you end up with something which is completely coherent. It is not incoherent at all. And that will tell you that you need to draw the number of samples even more than full sampling, which doesn't give you very much. And we argued that that's actually the reason why you get complete garbage here when you do this uniform random sampling. Then we argued that you could do different kinds of samplings and you would get different kinds of output. And what we're going to try to do now is to figure out what is really going on under the hood. And I just want to mention this, because this is a very important part, that this barrier that essentially you get, the incoherence barrier here, comes from the fact that you have a truly infinite dimensional problem that's sort of lying below here, that we do discretize, but when we actually deal with, say, MRI, it is an actual Fourier transform that we have. And if you look at the limit here as n tends to infinity, you actually get this infinite matrix. OK, so we talked also about the idea of having a slightly more general setup for sparsity. And we argued that if you look at images and you look at the relative sparsity in each level, you can plot them, and you will see this kind of behavior here, that for a fixed epsilon, if I let my number, the levels grow, actually the ratio between the important coefficients and the length of the level tends to 0. So things become sparser and sparser as we move out in the different levels. And we did this example here where we said, actually, if I keep the fraction, the 15% steady, I'm getting an interesting phenomenon that when I blow this up, I'm getting better and better results. I'm getting more and more for my money. So when I look at the relative error here, it drops down to 6%. And you can also see the quality here of this part of the image compared to the first one, which is really complete garbage. So there's something going on here. And then we concluded by saying that we wanted to have a sort of compressed sensing 2.0, which we have to have a general setup for the pillars. And the pillars now should essentially be replaced by just putting the word asymptotic in front of it. Right? So we're going to talk about asymptotic sparsity, and we're going to talk about asymptotic incoherence, and then we're going to do multi-level subsampling. So this is how far we got before lunch. And I said that a natural way to define this kind of level sparsity is simply to take the structure that you have with xlets, okay, with the levels, and instead of having one number describing the sparsity, it should be a vector. And that vector contains the numbers S1 through SR. So if I have R levels, then in the first level, I have S1 important coefficients. In level 2, I have S2 important coefficients, and so on and so forth. And these guys here could typically be the ones that we had on these plots, these guys here. So if we see that an image is clearly going to have a nice sparsity structure and asymptotic sparsity structure, meaning that when I let my numbers of levels go to infinity, or become larger and larger, the fraction here becomes smaller and smaller. So the definition of sparsity in levels is not in any way a controversial one. It's what you would expect to do, right? So that's the definition of sparsity in levels. Now, that means that we need to change the setup a little bit, because that means I'm not going to be able to recover arbitrary sparse signals anymore. So remember we had this k-term approximation. It was this sigma, and it said simply something about how close I could get to a sparse vector. How well could I approximate my vector with something which is sparse? And I'm going to change that a little bit, because now there's an extra structure. It is not just sparsity, but it's the whole S vector. So I call now, we did that in the previous one, we call the set of SM sparse vectors sigma SM. So now the best SM term approximation of your signal is simply now the minimum that you're getting here if you're approximating your beta with something which is SM sparse. So I'm just taking the previous concept and extending that to this structure. Did that make sense? Hopefully. All right. So how are you going to sample? And the way we're going to sample is that we're going to sample also with a multi-level structure. And this will be very clear when we go back and look at the actual image of the structure later on. So the way it works is that I'm going to have R different indices that essentially give me the indices of my levels where I'm going to sample. And then in my level, kth level, I'm going to have an omega k. And that omega k is chosen uniformly at random. And I'm going to choose that with size mk. And then my total sampling is simply the union of these omega 1s through omega r, right? And keep the plots that I've shown you before. Keep this block diagonal structure in the back of your head, right? If you had a perfectly block diagonal matrix, how would you have sampled there? You would probably have taken samples according to that block diagonal structure, right? So the first block, well, there you have omega 1. The second block, you do omega 2, and then so on and so forth. So it's not a complete accident that I set it up like this, right? So what I have now is that I have a level structure in my signal. I have a reasonably block diagonal-ish structure on my matrix. And that's what I'm adapting here, and that's how I'm going to control my sampling, which I'm now going to choose according to the structure of my matrix and my signal, right? Okay. This will typically be a 2D R-level sampling pattern. In this case here, this is in frequency. So this would typically be, so 0 frequency is here. And you can see sort of the level structure in the circle here. They don't have to match the wavelet levels perfectly. The theory doesn't tell you, but the theory will be about wavelets. But this one here actually doesn't fit it perfectly, but pretty close. So you see the level structure here, and it's actually, this is about, I think it's 50 levels. And you have the same size of them all the way down here. So it is hard to see from the projector, because there are actually points all the way out here. Now, if I changed my MKs differently, that pattern would look differently as well, right? And that allows me to tailor my sampling pattern according to the structure of the signal. That's the key part. Okay. And now we're going back to this plot, which I've shown you before, where I've shown you the absolute value of the matrix, which is now the matrix that I get. So this is the discrete Fourier transform combined with the discrete wavelet transform in 1D. And I put 0 frequency here. So when I plot now the maximum values of this matrix, that is essentially the coherence or incoherence plot. In the classical theory, you should have had one essentially dark color. It should have been uniformly flat, like 1 over n. But you don't have that. But the nice thing is that it's clear that it's a pattern. So in the beginning here, there is a 1. So white is 1 and black is 0. And then it gets more and more incoherent as you go out. That sounds like a pretty good deal, because that's what we want, right? But I also argue that you have to be a little careful. If I change from, I have the same measurements, Fourier, but I change this now from wavelets to Legendre polynomials, then suddenly things change. And you see the local incoherences change dramatically. So that means that if we're going to analyze this from a theoretical point of view, we need to have an understanding of what local incoherence means. So what this is, it's really taking the idea of coherence, as we've discussed before, which was just the maximum values of the matrix squared. And that is sort of a sledgehammer. And what we're doing now is that we're creating a scalpel out of that sledgehammer by looking at what are the large values, sorry, what are the maximum values of essentially small sections out of that matrix. So here I have projection. So I have this is the sampling levels, and this one here will be the reconstruction levels. And here what I have are the projections. So this one here projects from the k minus 1 to the nkth part, and likewise from L minus 1 to L. And I multiply these things and take the root. And this gives me a number, and I call this the local coherence. And what it measures is that it measures things like this. That part, that part, that part, that part, that part. And the whole thing is that when I'm actually going to look at how I'm going to sample, I need to see what the values of the local coherence is, and that will show up in the estimate. So we're going to pretend that we can solve the L1 problem perfectly. And then what the theorem says is this. It tells you that if I have a level structure in my sampling, and I have an SM sparse vector, then I need to draw in each level an estimate based on this. So now you see I need to sum up these local incoherences with the local sparsities. Right. So if we go back to the traditional case, then there would not be a vector here. It will just be a number, and it will be mu times s. But this is much finer because I have to sum up now with the different local sparsities and with these incoherence parameters. And when you have that your multi-level sampling scheme with these m's now satisfying this estimate, then you have this estimate on your recovery, and it will tell you that here is the noise parameter. There is an L here. You have to pay. This is the root of S. And then you have the SM term approximation. So in other words, if the noise is gone and you have a perfectly SM sparse vector, then you get 0 in the error. If you don't have something which is perfectly SM sparse, well, you have to pay for that in this error term. So this is very close to what you'll have in the classical setting, but this is now done for the level structure. So this looks horrendous, doesn't it? So I'm going to make it a little easier, because you can estimate these things here locally, and you can get a much nicer form of this. So in the case of Fourier, discrete Fourier, and discrete wavelets, this is what you can get. It will tell you that the kth level you have to sample according to this estimate here. And that means that it is dominated by the kth sparsity. And then you have exponential contribution from these off-diagonal parts. So what it tells you is that you have a little bit of interference from the other levels, but it is exponentially small. And you can actually see this. So now I'm going to go back to the image. I have advocated this almost block diagonal structure. So the reason why you get this kind of estimate with these exponential terms here is because, you don't have complete 0 here. If it was completely block diagonal, then these guys here would disappear completely. There would be only the kth sparsity. Does that make sense? So in fact, if I look at this image here, and I look at Hadamard combined with Har, It's perfectly block diagonal. And if, well, there's actually, the theorem here actually holds for Welch functions as well. But in that case, these guys here would be completely gone. And it would tell you that if you sampled with this matrix like that, you will have your first level, your second, your third, your fourth, your fifth, your sixth. And you should sample then locally in each, the kth level, if you will, according to the sparsity at that level. And this here will be the incoherence, which actually goes like 1 over n. And that explains this part here. But there's another cute little thing that I want to point out. And that is that I have two parameters which I haven't told you what is. There is an alpha parameter here, and there is a v. And for those who know wavelets well, this alpha here is related to the decay of the Fourier transform of the mother wavelet. And this v here is the number of vanishing moments. And that means that if you have the Debussy wavelets and you go higher up, this here will increase, and so will v. And that suggests that the terms here are going to go quicker and quicker to 0. And in fact, that's exactly what you see. Oops. If you look at this image here, you can see this sort of blurry part here. Now, this is for Debussy 2, and this is for Debussy 5. And note here that is actually getting closer and closer to a block diagonal structure. This is exactly what the theorem predicts. So if I continue this, you would have seen a matrix that becomes closer and closer to a block diagonal structure. And that's exactly what is going on here. Then the contribution from these other parts of the sparsity gets less and less important. So now, I claim that with these tools, you can perfectly well understand compressed sensing in inverse problems. Because now if we look at the image, this is the image that I have, right? And I look at the wavelet coefficients. They are distributed like this. And I have a matrix which I end up with, which is almost block diagonal. That means that if I have a specific structure here on the wavelet coefficients, I should be able to know how I should sample. Did that make sense? So in other words, if I have done the flipping, that means that I put these guys here at the very bottom, right? So if I were to have a sampling pattern that should be able to take a signal of that form, well, I have to sample completely differently. I have to sample a lot in this part here, because here there's tons of coefficients. So if I have a sampling pattern where I favor this part here in the top, and I would use that on a signal which had a completely different structure, I would get complete garbage. And that's what happens with the flip test. So you take a reasonable sampling pattern that describes this structure here, and that means that the types of signal that you will be able to recover is going to be something of this form here. And that's the key part. So if you can understand this image here, then you understand compressed sensing. OK. Any questions? So what can we do? Can we use this now? Now, you see, if we simply just look at this image, which I claim can make you understand compressed sensing. If I look at this, if I have that, here I have important coefficients a lot, and there's not that much sparsity. Out here, there's tons of sparsity. And here I have a matrix which is locally very coherent here and very incoherent here. What that tells me is that these two asymptotic structures align beautifully. So out here, things are very incoherent. And here, my signal is also very sparse, right? And that's an important thing. Because if I was going to do if I had a budget and I was going to do 15% or X%. Now, if I had an image which was at low resolution, that means that I'm in this area here. You know, suppose I do like 256, right? I'm in this area here where things are going to be not all that incoherent. And the signal at that dimension is going to be, well, not all that sparse, right? And that means that if I have a budget at a low resolution, I won't be able to do very well. It's not because I'm not smart, it's because there is a barrier here. So actually, when you saw some of the initial papers in compressed sensing in MRI, they did low resolution. And the improvement, the time saving that was done on these examples were not that great. And it wasn't because people couldn't do this right, it was because there is a barrier here. At low resolutions, things are not very incoherent and things are not that sparse. But at high resolutions, things really work for you. So when we go back to this Berlin Cathedral example, it makes perfect sense, right? What I'm doing here, this is a 256 level. Well, if I looked at the wavelet coefficients of that image now, there are going to be quite a lot of them, and they're not going to be that sparse. And if I look at the matrix that I have, the Fourier to wavelets, it's going to be pretty coherent. And when I blow up the resolution, what that means, oops, is that I'm in this regime here. I'm taking more and more stuff here, and things become nicer and nicer and nicer. So that is why, oops, we do get this nice effect that when I blow up the resolution, I will get better and better results. There is nothing magical about this. It is a very natural thing. But what that tells you is that if you want the max effect of your compressed sensing, you have to go for high resolution, which sounds like a tail-chasing argument, because if I wanted to reduce the amount of measurements, I have to take a lot of measurements, right? So I'm going to show you a couple of other examples just to digest this a little bit. So I'm going to show you now, this is in some sense a real-life experiment. It's not a toy image like the Berlin Cathedral. This is an actual MRI experiment. And I'm going to blow this up to very high resolution. And I can do that because I'm using a pomegranate. And you can't do this actually with a patient because at full resolution, which I'm going to show you, which is at more than 2000, it will take you 12 hours to scan. And humans have this bad habit of breeding, and that means that you will actually have a distorted image, whereas a fruit is going to stay still for 12 hours. So this is not an experiment that I recommend you run on patients, but you can certainly do it on a fruit. So this is with real MRI data, and I'm showing you the subsampling pattern here. Okay? So here is the original, and we're going to stay with 5%. So there's a fixed budget, and I'm going to do exactly as I did with the Berlin Cathedral, but this is with actual data. So watch the error, and watch also the quality. So it does improve a little bit. Now it improves a little more. And now I have deliberately not shown you which one is the original and which one is the subsampled. So now you can guess. It's hard for the human eye to spot, right? So that's the point. I mean, you can get that quality. So if you want to impress your colleagues, that's what you pick, right? You don't pick this one. They're not going to be impressed. They're going to be really pissed off. And certainly the radiologists are going to be pissed off if you show them something like that. But they're going to be very happy if you show them something like this. But there's a catch. I mean, I can't do that on a standard MRI machine. So if you're going to do this in practice, you want to do something at lower resolutions. Because I can't really do 2048. I could push it to 1,000, potentially. I mean, don't get me wrong, this is done on an MRI machine, but it had the full sampling done here to the comparison is done, it takes 12 hours. So that's why you can't do it. But of course, this is 5%, so it's 20 times speed up of that. But still, 20 times speed up of 12 hours is still substantial, right? So what do we do then? If it tells us that you should go for high resolution to get a real boost of compressed sensing, but the goal of compressed sensing was to take fewer measurements, how do we actually cope with that? And the idea is as follows. Why don't we try to do a slightly different problem, namely, I would like to enhance my resolution. So if I'm going to use a fixed budget, instead of trying to subsample from an image of low resolution, why don't I say I'm going to take the same amount of samples that I would do at some resolution and try to enhance it? Because I want the asymptotics to work for me. Did that philosophy make sense? So I'm going to show you a completely synthetic example. I've taken, this is a very neat little phantom. It's created by these guys from Switzerland. It's Prusman from ETH and Michael Unser from EPFL, and these were their students, Gurkin Kern and Lejeune. And the reason why this is a very neat test example is because you can actually compute the true Fourier transform of this. It's an infinite resolution image, and it's actually defined through Bezier curves. So I can actually model the MRI machine very well with this. So what we're going to do is that we have hidden a little brain tumor inside the phantom. And the task for us is to figure out, to see the brain tumor. Okay? And this is what you will see with standard full sampling. So I've now sampled a 512 by 512 full in frequency. And I've tried to recover that. And this is simply just by inverting the FFT. And I'm getting this image back. And this poor patient of ours is a completely synthetic experiment. There's no patient, actually. But this synthetic patient is suffering from a really sophisticated and bad cancer. And it's so sophisticated that the tumor cells actually form a sentence. And the only cure for the patient is that you need to read that sentence. Can you read it? No, you can't. So what we're going to do, right? So now we've spent our budget. We have done this. There's a lot of samples here. And since I can't see what this is, then either I have to put the patient back in the scanner and go for a higher resolution, which is going to take a lot of time. But I'm not going to do that. What I'm going to do is that I'm going to take the same budget, and I'm not going to do full sampling at 512 anymore. I'm going to take the same amount of samples and throw it on larger frequencies. I'm going to essentially subsample from a higher resolution. And I want now the asymptotics to work for me. And now what do you think happens? Fantastic. So I am subsampling now 6.25% from a much higher resolution, but I'm using the same budget. I'm not using a longer scanning time. I'm enhancing the resolution. So now suddenly compressed sensing works for me. I haven't tried to save time. I have used the same budget, and I have allowed the asymptotics to help me, because now I can get better results. And now I can save the patient. So that's what you may want to do. OK, so I'm going to tell you a little story. And I'm going to initiate that story by asking the question, will compressed sensing ever be used in commercial MRI scanners? That's a reasonable question to ask. So we put this example here on the archive sometime in 2013, I think. And we actually did the theory first. We cooked up the theory, and we said, with these results here, I can predict that instead of taking full samples here, and when I distribute this in a higher resolution, If I know something about the distribution of the sparsity in wavelets, which I do, I will be able to say that with the same amount of budget, I'm going to do better at a higher resolution. So that was a prediction. And we did this phantom experiment. And we thought, why don't we contact a manufacturer? It'd be kind of cool to implement it. We were mathematicians, so we didn't have an MRI scanner at our hands. So we wrote a letter to Siemens. And it took a little while. And we essentially showed them this, and we wrote a little note where we detailed the synthetic experiment. And it took quite a long time, and we sort of climbed higher and higher up in the hierarchy. And eventually, we got the head guy of Siemens Medical Imaging on the phone. So he said, well, essentially, thanks very much for getting in touch. We appreciate that. But we have already implemented your stuff on our machines. So they saw the paper on the archive, and way before we contacted them, they'd already implemented it. And they said, well, we've even written a report about it. So this is the report they wrote, which was excuse me, published in the Proceedings of International Society for MRI. And they were pretty happy about it. So they concluded that the image resolution has been greatly improved. And they also concluded that to get the full potential of compressed sensing, you really have to use the asymptotic sparsity and asymptotic incoherence. And therefore, they conclude it might be better to use compressed sensing to increase the spatial resolution rather than accelerating the data acquisition if you're doing non-dynamic 3D MRI. So indeed, that was an interesting thing. And I'm going to show you the report. So now I'm going to do an interesting exercise because I want to actually point to the report. I'm going to try to show you some images. Can you see? Okay, so what I want you to see, can you see? Oh yeah, excellent. I want you to look at this. This is the actual sampling patterns that they're using for this experiment, and it's with a real patient. And what you see here is the standard Cartesian sampling that you would do. You only see a slice here. This is a 3D sampling, so you only see a slice of that. And what they're doing exactly what we suggested in the synthetic experiment. And the important part here is that it is really the time scanning which has kept the same thing. And that's very important because it's not just any sort of subsampling ratio which is important here, it's the actual time. That means, you have a stopwatch, say how much time does the patient spend in the scanner, and then now the scan is over. That's the only thing that these guys care about, is the actual time. So if you run that scanning pattern, or that one, and that one, and that one, it takes the same time. So they try that. And you see exactly what they're doing here. They go higher in frequencies and take subsamples from a larger area of what they call K-space. If you talk to an MRI engineer, you need to get accustomed with the K-space term. That just means Fourier frequencies. Okay? And that's what they're doing. And then they have, you can't really see, that's the problem because it's hard to see here. But then this is the experiment that they do, and they conclude that this is what you will get with a standard sampling, and this is the improved part that you will get with the resolution enhancing, right? And you can argue, and this is where I'm not 100% sure if they say that the resolution has been greatly improved, because to me, it is okay. I mean, I do see there's a little bit of blurring here. You agree, right? And then there's a little bit of improvement here. But although they used the word greatly improved, we didn't think it was that great. I mean, they show the phenomenon. But what we did was that we looked at this sampling pattern. And this sampling pattern here, which I think they have patented now, is simply a 3D spiral that they do. And you see it heavily favors the samples here around 0 frequency, and then it spirals out. It's a little hard to see it actually here on that screen, but it is not just a dense thing in the middle. It does spiral out. But you see, when we saw that, our conclusion was immediately, this here is not optimal. And no offense to the Siemens guys, these are very smart people and they know much more about MRI machines than we do. But we suspected that this sampling pattern here is not at all optimal. In other words, they have not read the paper and say, this is how you should actually take your sampling pattern. What they did was that they took a sampling pattern that they could create from a previous code that does give you a kind of spiral like this, which is great, but is not in any way optimized. So that's why we want to say, well, if that's what they're doing, why don't we get our hands on an MRI machine ourselves, right? Because we had a theory to back us up. Okay, and now I actually have to try to figure out how I get back to full. Oh, there we are. Yes, yes, yes. My French is terrible. So, now I'm going to go back to the very beginning. And that was the motivation for this experiment. So Siemens had been able to verify that what we predicted theoretically was that we felt that one could do better. So what we're doing is that we're doing exactly the same issue. We throw our guy. Well, I'm not sure if they actually did the brain. They might have done a knee. I don't care. So that was the motivation. So we're going to do exactly the same thing as they did, but we wanted to set the sampling pattern so that it was optimal. And what is going on in this part here is that you're not sampling from a high enough frequency area. You're taking your budget and you're not spreading it enough. You're wasting your resources on too low frequencies. The optimal sampling pattern for this is to go much higher, and the reason why is because at that resolution you're getting much, much more sparsity in your wavelets. So what Siemens did wrong is that they placed the samples wrongly. It is way too equally distributed. It needs to be much more of a cloud. And the question is, can you implement this? And you can. Because if you're doing 3D scanning, you can sample according to each line. That means that you can subsample as a cloud in 2D. So this is implementable. And that's why you can get this effect. And now, if you compare the Siemens example, where they conclude that you have greatly improved the resolution, well, in this case here, you do actually improve the resolution substantially. But you need to know exactly how to do it. So to get your optimal compressed sensing result, that is the key part. And here's what's going to become even more difficult, is that the optimal sampling pattern that you're going to do is even going to depend with resolution. So this here is done as a 256, and then I subsample from a higher resolution. If you do that in a different resolution, your optimal subsampling pattern will be different. So it's not just throwing something in and hope for the best. You need to know what you're doing. Okay. Did that make sense? It made sense. Good. Good, good, good. Okay, so I'm just wondering if we should take a quick break, and not break meaning that you should leave the room, but we should have some questions, because I would assume that there must be some questions. But I'm just going to end with a hopeful punchline. I'm sorry that my thumb isn't more efficient here. Yes, so I want to answer the question. Will compressed sensing ever be used in commercial MRI scanners? And we are closer than ever. And apparently now, both Siemens and GE have gotten compressed sensing FDA approved in the States for commercial scanners. So that means that it is highly likely, since it's now FDA approved, that the next generation will have it. The question is, are they going to use this for time saving or resolution enhancing? And also, what are the sampling patterns that they're actually using? That will be the question. And now you can go out there and you can cook up something which is competitive, because we have done this in some sense as a theoretical exercise. You can do this in practice and say, hey, I've patented this sampling pattern. Why don't you sell it to Siemens and see if they're going to pay for it, if they can actually get a better improvement? So we will highly likely see compressed sensing implemented. And yes, let's take a little bit of questions now, rather than very much at the end, because I'm going to talk a little bit about structured recovery. So this sort of has a natural ending point to it. Are there any questions?
So I was wondering, like, how close are engineers actually really to doing a random type sampling? Because I've heard that approximately a year ago, and there was exactly the same question. Like, you know how to do it properly, but in practice, I mean, this spiral sampling is something that they can do, I know that, or some lines or something, but this is really simple.
It is.
And so how close are they right now to really something which is appropriate?
So the example that we did is implementable. And this is it's a very good issue. Let me actually go back to the Siemens report, so I can just highlight this. It's a really excellent question. Now, this here is a completely deterministic sampling pattern. That doesn't mean that it's necessarily bad because it's deterministic. The reason why it's bad, no, I'm not going to say it's bad, but it's not optimal. It's because it is way too equally distributed in this area. If you could see this on my computer, you would see that it really doesn't have the correct sort of cloud shape where it goes like this. It is very much placed around here, and then it's pretty much equidistributed elsewhere. And it is not completely clear to me why Siemens wanted to do a spiral, because you can do line sampling in 3D, which you can subsample from, and that's implementable. And it's not that, so the budget that you have for K samples, it is only the time you're paying for doing one line sample here, and if you take the other one up here, that doesn't cost you more. So for some strange reason, Siemens wanted to do a spiral one on the total thing here. So to answer your question, if you do line sampling, you can implement it. But, and here's a delicate issue, do you want to do some randomness? Maybe a little bit. Are people going to do that in practice? Unlikely. What you want to have is a all-rounder that says essentially on this type of resolution and these types of images, this fixed sampling pattern is going to be a pretty good one. It may not be completely optimal, but it will be better than that one. And then you can ask the question, if you want to do a spiral sampling, how do you make that optimal? And that is essentially up to the engineers. And to answer your question, I don't think that is clear. But what they have done now for the FDA improvement, I assume is something a la that. So they have a fixed pattern for which they essentially hit return. The scanner does that. And it gives you some improvement, but it may not be optimal. And then it's going to be the question of the sort of engineering versus math. How much are you going to spend on trying to improve this to the absolute maximum? Or are you going to settle for something which may not be optimal, but still pretty good?
So this sampling is a 3D sampling too, or is that a 2D sampling?
No,
because
this is a slice of a 3D spiral. So the spiral goes like this, but you can only see a slice here. So everything is in 3D. And I should also say this, there might be people who are experts in MRI. Doing subsampling in 2D MRI is not that crucial. And the reason why is that taking just a slice doesn't take that long time. But taking a 3D takes a long time. That takes 15 minutes on a 256. So what you're doing if you're taking a 2D slice, you're getting a much more noisy image, but it's quick. So in that case, you can actually do full sampling at a higher resolution if you want to. So it's really the 3D part which is the most crucial issue. I just want to mention in passing, if you want to do this in dynamic MRI, then you have a third dimension, namely time as well, for which things become very sparse. Because if you look at a video where you essentially have the same kind of image each time, Well, there's a lot of sparsity in that time domain. So you can also, but I'm not addressing that. And then you can put that on top and say, how do you actually sample in space here to get the most optimal one? And how do you use some kind of sparsifying transformation in time as well? So, but very good question, but I simply can't answer and say, yes, I know, but it's in the developments.
Oh, that was a good answer, thanks.
Is there any questions?
Hi. My question is, when you introduced this best K approximation, this sigma
Yes.
quantity at the very beginning,
Yes.
you had an analogous object in the multi-level sparsity
Yes.
case. In the non-multi-level case, you had P norm,
Yes.
and the other time on the multi-level case, you had one norm.
Yes.
Does it have any reason, or
No,
where
absolutely.
does it
You're
appear on
absolutely
the?
right. So no, you can put any P norm on it. But absolutely. So in this case here, I'm just going to go back to it.
It was 64, page 64.
No, it's a very good point. It is not any sort of lack of generalization in this case. Where did I put it here? I put it there. Yes. So if I wanted to put a P here, I could do that as well.
So it doesn't matter.
So
Okay.
it doesn't matter. So you can measure your sort of signal decay in whatever P norm you want. So that's not a, but it's a good point.
Okay,
Absolutely.
okay, thanks.
Question again?
Okay, so that's great. Let's wrap up this part now. So I have 40 more minutes. I may not be able to cover everything, but that's not the end of the world. I could do a little bit of this tomorrow morning as well. Okay, so now I've talked essentially about structure in the sampling part. And I promised you that I was going to talk about compressed sensing and structure in general, and now I'm going to talk about structured recovery. So if you Google structured recovery, you'll find quite a lot of work on it. And the premise of the question now is slightly different. It says, what if I have sampled with something that is completely uniformly random? And it was motivated by the following experiment. You take your favorite image and you sample it with a Gaussian matrix and you try to recover it with wavelets and you get this. And the reason why that happens is we can sort of intuitively understand what that complete randomness in say, a random Gaussian does to your image. It takes all the structure and makes it completely random. So if I look at essentially the wavelet coefficients, if I take a sampling of my image with random Gaussians, then I don't favor any parts of the signal at all. I just pretend that everything is completely arbitrary. And that means that it squashes all the structure away. So that's why you get this kind of result, and people wanted to improve that. Because everybody knew that wavelets give you a lot of structure. So if the premise now is that you're given measurements that are uniformly randomly chosen like this, and you don't have a choice, then what should you do? Can you improve things by changing your optimization problem? Right? You don't have a choice in the sampling anymore. You're given, right? But can you improve it? So that's the premise of the argument. So I'm just gonna, this list here may not be complete, but you can trace this even back to the early work of Donahoe, and then you have a lot of people that follow up on this. You have the approximate messing passing that came out, and there was an influential paper by Donahoe and Malek and Montanari on this, among others. And this have resulted, I wouldn't say, yeah, it's almost an industry now. There's quite a lot of different algorithms out there that are not based on solving the L1 problem. Because this here is created by solving the L1 problem. Right. So maybe, well, I wouldn't say the most famous. I'm not going to rank these things in terms of fame, but one of the earlier ones that got quite a lot of attention was the approach that came out of Rich Baranuk's group at Rice, which is called model-based compressed sensing. And the idea essentially came from compression, where people had said, well, can you improve your compression by taking extra structure into account? So there's a tree structure also, which I haven't described for wavelets, which is very well known. And could you utilize that in your compression algorithms? And then could you see a difference? And people could see some difference. So the idea was that, well, let's try that in compressed sensing. Right. You have a quite different approach. This is the Bayesian CS that comes from Larry Karen's group at Duke. And I'm not going to get into the details because you have to have a sort of a full talk on each of these different approaches. And then you have the turbo amp, which Simon Schneider, so Phil Schneider is now, I guess, sort of the Papa approximate message passing guy. But what all these algorithms do is that they essentially try to go and take another extra level. Like the L1 is agnostic to any tree structure on the wavelet coefficients. It tries to use extra structure on your recovery algorithms. And the point here is that you assume something which is completely random, like a random Gaussian, and then you are utilizing that in your algorithm. And these algorithms here are completely different, but they come from the same philosophy that you will like to utilize extra structure. So it is of interest to see how they do. And I have put errors here, but note this. The error here is in L2, and everybody knows that L2 error is a crap measurement for quality of images. So that should really be taken with a pinch of salt. It is the eyeball metric that counts. And I'm going to leave it to you, and I'm not going to suggest that one is better than the other one. But this was actually the one that came from the paper. And here is the standard Gaussian. And this is the model-based compressed sensing approach. You can do this with, of course, all the different algorithms. And I have deliberately now done this with a reasonably low subsampling ratio so that you actually see the effects. So this is the standard L1 recovery. And then you have the different ones, but you should take into account that the error here doesn't really reflect what the image quality is. That is the eyeball metric. But what I do want to point out is this, that if you, instead of taking your complete random measurements and then try to put structure on your recovery algorithm, it is more beneficial to simply do structured sampling and then do classical L1. It is a completely unfair comparison, and I'm not suggesting that they should be compared because this here is a different set of measurements. And the premise for these here is that you're given random samples, and you're going to try to essentially correct for that by introducing the structure. So I'm not suggesting that this here is a fair comparison. This is a different setup. But it does essentially raise an interesting question. And we had people writing to us asking about, should we try to change the MRI machine so that it could be more like a random Gaussian? And this was pretty early when the sort of S log n gospel for random Gaussians were pretty solid. And people were asking, so maybe we should try to change the MRI machine so that it gives us something which is closer to a random Gaussian. You won't be able to implement that perfectly, but it's at least something that is closer to it. And the answer to that question is no, no, no. Actually, the Fourier measurements is great because magically Fourier frequencies and wavelets match beautifully together. So you should never try to change that. You can make the argument that what if you put some of these algorithms here on top of that, what would happen? That's not completely clear. So you could do structured sampling and structured recovery on top of each other. But I just want to emphasize this. I'm not comparing this with these guys here because it's a different premise. But I do want to emphasize that one should not try to change the MRI machine. The MRI machine gives you Fourier coefficients, and it's a great thing to have. So you can do a similar plot with different images, and we'll see a similar effect. I just want to make a little note, because I'm going to talk about this image here in different contexts. And it is in relationship to comparing different methods. And I want you to think about the following. How can I guarantee that when I have actually computed these things, that I know that the algorithm that I've used to compute this actually gives me an error for which I know and can control, and that the performance of the method here is only due to the method itself and not me being a very clumsy coder? Because these are completely different methods, and if I'm going to compare them, how can I actually say something about them unless I can actually guarantee that what I did numerically here actually computes something reasonably accurate to, say, the oracle that should give me that solution? I want you to keep that question in the back of your head, because I'm going to address that tomorrow. Okay. Okay, so now I'm going to, because I mentioned a little earlier today that I wanted to talk about other xlets. And this is also of interest because you would like to squeeze more out of your problem. And the other xlets typically gives you a sparser representation. So here is also a comparison. This is not with structured recovery. This is all with structured sampling. But I have done this with different representations of my signal. So this is the classical wavelet. And here are curvelets that you may have heard of. This came out from Stanford. This is Manuel Candice and David Donahoe. Shearlet is, I would say a TU Berlin sort of close hole. And I've also done total variation. And now you can ask, which one is better? But I should warn you, I could have taken different images here, and you would have seen different. It's not always that this one here, that Shearlet's beats curvelets, for example. And this is also in the L2 norm, which really isn't a great way of measuring your error. But I want to point out the following. When you're changing your xlet, your structure also changes. Not dramatically, but it does. And that means that your optimal sampling strategy now also changes. And if you're sampling, and the biggest difference is probably when you go from wavelets to total variation, it does change. Wavelets and total variation are quite different. So to make even more complex stuff into your model, actually if you change your xlets or your total variation, you actually have to change the sampling pattern as well, if you're going to make this optimal. Right. Finally, I'm going to wrap up by trying to understand what we've actually said theoretically. And eventually, finally, I'm going to do a little bit of total variation. And the question that I haven't asked, and certainly not answered, is why do we really see this benefit of this structured sampling? Because theoretically, I haven't shown that. What I showed you was some S log n terms where I sum these SKs up with these local coherences. But I actually didn't show that I would beat the random Gaussian S log n estimate. I haven't shown that. So theoretically, it's really not something that tells us that this structured sampling is going to be beneficial. Just going to go back to the estimate so that we recall that, so we have that fresh in our minds. Yeah. So when I sum this up, I have exponential terms here, and that's why I can sum them all up. But if S now is the total sparsity, so that's the sum of S1 through SR, the total number of samples is still S log n. So I haven't actually fully done my job here. I have waved my hands and I've showed you pretty pictures, but I haven't really shown you why we do better, right? And that's what we're going to try to do now. So I'm going to wave my hands a little bit. Where are we now? Yes. And I'm going to try to advocate why we're actually going to get better results than you do with a random Gaussian. So for random Gaussian, it is that constant here is known. It's 2 and then s log n over s. And the only thing that we have done so far is this estimate here. So what is going on? So let's try to understand this. So I'm going to take a piecewise smooth function. So think about that this is here is like a slice of an image, right? So this is my piecewise smooth function, and I'm going to try to sample it. And this is how it looks if I sample. So I pretend that this is sort of a discrete signal. And what you see here is now the magnitude here of the Fourier transform of it. And here is the measurements that you will see if you hit it with a random Gaussian or a random Bernoulli. And it squashes everything out, which is to be expected, right? Now, why are we actually doing better? And the reason why we're doing better is as follows. So I'm going to show you a 2-level sampling scheme because it's a little easier to explain it with that. So a 2-level sampling scheme, which is just a special case of this k-level sampling scheme, says that if I have this condition here, so what I'm going to do now is that I'm essentially going to fix my M1, that's sort of the first level, and then my N1 is the number of samples that I take fully. And if I have this condition here, then it says the rest that I need for the rest of the part of the signal, my M2 has to satisfy this, and then I get this little mu N1 times S2 here. So the key thing is that if I could guarantee that this here holds perfectly, if this would be 0 even, then I only need to worry about that part here. And what is going on, and I'm totally waving my hands because this is actually a little more involved argument, but I have a finite amount of time here. To get this here satisfied, you essentially only need a linear relationship between the number of wavelet coefficients and the number of samples Fourier. And that means now that essentially the S sparse vector, or the sparsity S vector, has all these M1 coefficients, the full thing. And I'm not paying more than a linear factor. So what I'm essentially getting is that I'm getting these first things almost for free. I'm not getting for free. I'm sampling everywhere here. And that corresponds to getting essentially all of the wavelet coefficients in that level. And that means that I'm not paying a log factor for this in total. I just have that. Whereas for the Gaussian problem, I actually have to pay a log factor on this part here. And this is the part of the signal which is super important because that's where you have all the energy of the signal. This is where you have the coarse wavelet coefficients. So if you're going to have a bunch set, you desperately want these guys. So when you're actually sampling with a completely random vector, you are distributing this completely randomly like that. Whereas if you do this, you can go back to my favorite image again. Here we are. I'm not actually going to make the first level, and the gentleman up there also asked about this before lunch. So I'm actually not going to make that the first level. I'm going to take essentially all of these guys here. I'm going to do dense sample here. And what that corresponds with the wavelet coefficients are these guys here. And they're big and important. So if I'm taking that chunk here, then I'm getting all of these guys for free. Well, I'm paying exactly the same amount. And if I did that with something which is completely random, I have to pay a log factor. And if that log n is typically 10, whoops, that's a lot. So that is what's going on. So the reason why you do better is that you're getting these things for free, because you're always sampling densely there, and then you're getting the S log on the rest of the part. And that's why we're actually doing better than the S log N. Much, much better. Did that hand wave the argument make sense? Sort of philosophical? Good, good, good. Right. So, you could ask if the model that we have cooked up is the correct one. I have waved my hands a little bit and said there's a level structure on the signal, and hence you should go for it. But is it really the correct one? Could it be that there would be some other structure that would be actually capturing this better? So what I want to do now is that I want to check the model. And if I have done this, I did this morning. Yes, I did. Thanks. I did it correctly. What I'm going to do now is that I'm going to show you the flip test over again with a slightly different images. And then I'm going to do the experiment. I'm going to redo the flip test. But now I want to check if my model is reasonable. So I'm going to do flipping, but I'm only going to do flipping in the levels. Right? Did that make sense? Because I am claiming that you should work with the level structure if you're doing wavelets. And inside each level, you're going to have, in some sense, randomness in the coefficients. They're not completely, because there's a little bit of a tree structure here, but roughly. So I'm claiming that this is a reasonable model. And to do that, I'm simply going to test. So what I'm saying is that if you have a model for your structure, the way of testing if this is a reasonable thing, do the flip. You can do this with anything, right? So what I'm going to do now is that I'm going to do the standard flipping first, and then I'm going to flip inside the levels and see if I actually get a difference. So here is the classical flip test, which I've shown. This is what you expect to get garbage. I just want to point this out. This is a little fascinating. Here I have sampled 97%. And still, if you do the flipping, you get nonsense. And can you see why? Can you see why? Even with 97%, you're getting complete nonsense in the flipping. You would think that when you're taking that much, right? This you could probably understand, but this doesn't seem right. But think of it. What this means, if I flip my signal, the corners here that I haven't done here are now the finer frequencies, right? If I flip my signal now, I put all the important wavelet coefficients corresponding to the fine ones, the fine Fourier, right? So I don't see them. That's why I get garbage. So the only way that I could do a flip is if I actually see 100%. Because if there's a, please.
You're a bit harsh there, because you could just do a random permutation, right?
Oh,
if
absolutely.
If you do just a random permutation,
yeah.
it would be better.
If I do a random permutation on that,
yeah.
Absolutely. But that means that there would be something in here. Absolutely, yes. So the lady suggested that I've not been fair. I do admit that I haven't. So this is a complete deterministic sampling. It's not random. So if I did now a random one there would be something here that would rescue me. But I've been a bad boy, and I've taken a sampling pattern here just to highlight the issue, where I haven't put anything here, and that's why you get nonsense when you do the flipping. Right. Okay, and you can do the same thing over and over again with the different images, and you will see exactly this phenomenon. So now the question is, what would happen if we flipped, but we only flip in levels, right? So I'm going to take my favorite signal now, but instead of flipping it from here to there, I'm now only going to flip these guys here inside the levels, right? And then what do you think happens? Well, actually, I have a slide here that explains this. So my ZF, I haven't actually shown you the image, what it will look like, but I'm going to take these guys here and flip them, and here, actually, I didn't have to flip them. I could just do arbitrary permutations of them, right? What do you think happens? Any prediction? You are actually getting the right thing. Now, of course, just because I show you an image, that doesn't mean that. But you can run this with a lot of different permutations in the levels, and you will see that it matches pretty well. So the level structure is a guess, but it also suggests that it's not that far away from the truth. So if you guys go out there, and I'm not saying that you should always use levels. Levels is of interest in when you use xlets and images. If you have other structures on your favorite signals, fine. Work with that, but use the structure. And if you want to test your model, use the flip to see, is the guess a good guess? And if you can do flippings inside whatever structure you have, well, then that suggests that you're in the right path. And it's not a great surprise that you also get these results. So if you can do the flipping, and if we agree on this sparsity structure that we have in levels, maybe we can go back to the restricted isometry property. Because we essentially said that the restricted isometry property is something that you may not see, because the restricted isometry property would say that you can do flipping. But why can't I just do the restricted isometry property on the structure that I have now put on the signal? That makes sense, right? So instead of just using sparsity, I'm now going to use SM sparse vectors. So what we simply say is that you have now the restricted isometry property in levels or in the structure that you favor of your signal. And simply says, well, if it now works like a local isometry on the vectors that have this kind of structure, well, we call that now the RIP in levels. And it won't be a great surprise to you now that with that kind of structure, then you can recover SM sparse vectors. But not arbitrary vectors, but those that are SM sparse. This is a weaker condition than the general RIP. It's a generalization, so the standard RIP is a special case of this. So to be able to do the recovery theorem, which I'm going to show to you on this slide here, I have to put in a couple of restrictions. And one is that the sparsity pattern has to have some kind of control. If I look at the ratio between these different SIs and Js, it has to be bounded. Moreover, I also have to have that it's less than infinity, and I also have to, well, this is sort of a trivial one, ML has to be greater than K, where this here is the size of the number of columns of the matrix, because otherwise there's a part that you don't control. And now, here is the final theorem. The theorem says that if you have a constant of this form here, and you have a matrix which now satisfies the restricted isometry property in levels, you can solve and you will get this estimate here, which is the same estimate as you get from the standard RIP, but it's now for this structured sparsity. But there is a catch. And that is the following thing here. L here is the number of levels, and here is this eta. And that is in the denominator. And that suggests that this here has to get smaller and smaller the more levels I have. And I also have to have a ratio between these SJs. That is an unwanted thing. And now you can ask yourself, is this because we were not able to prove something which is better? The delicate issue is that this is sharp. In other words, you can find matrices for which you have this satisfied, but with a different order here, and you won't be able to recover. And similarly, I'm wrapping things up now. And similarly here, with the number of levels, you will have these conditions, and you won't be able to recover. So this here, up to constants, is essentially a sharp result, which is a little irritating, I should say, but we can't do better. But at least you can have an understanding of the RIP in this structured setting. And with that, I see that people are almost falling asleep now because it's hot, and I have 10 more minutes. So instead of doing total variation, now I think we do a little bit of a question and answer session, and then I'm going to do a little bit of total variation tomorrow, and then I'm going to do the foundational part after that.
Thank you. Just for the last remark.
Yes.
Is it sharp for recovery or for having the rip?
Pardon me.
Is it sharp? This.
Oh
this
yeah.
condition?
So it's the point is that I can't. You could ask, is this just a mistake because we weren't able to prove better?
Yes.
And then we're saying that, well, actually, you have to have this. Because if you don't have, well, up to a constant. So there could be constants in front of here. But you have to have this asymptotic behavior in some sense.
Okay. So
To be able to get this recovery result. Because here there will be existence of matrices for which you have the conditions here, but you won't be able to recover. So
Okay.
it is not super sharp in that sense. I'm not saying that, I'm not giving you the coefficients here, but up to constants, the asymptotic behavior will have to be like this. So that's just too bad, but we can improve on it, if that makes sense.
But these SM, as I understand it, become exponentially when you have a big number of levels, because they are just they go to one with
Absolutely.
standard.
That's what I'm saying. So it's a bad thing.
Okay.
So, but I'm being honest. So the reason why we do this is that the natural question is, so you are claiming that we don't have the rip, and then one would say, but what does one have? And the question would then be, well, do we have something like this where there's a rip with the local structure that you're putting on? And then we say, so here is the local structure, it's the SM sparsity, and we're trying to prove it, and we end up with a result that clearly suggests that there's something going on, and then to say that, well, it's not our fault, then we say that it's some sense sharp. So if you have a different structure on your signal, you can cook up a rip for that, and people are doing that. So if you have a different structure, well, you can talk about a rip according to that structure, and then try to prove recovery guarantees, all of that. But there could be that you're ending up with something of this form.
Thank you.
I was wondering, can we apply this result on the previous matrix U that we had in the beginning of your presentation, where U is just a projection on P omega some sensing matrix and sparsity basis?
Yes. So this one here is if you just take away the SM sparsity structure, this gives you the standard rip. But this is actually a good point. It's a very good point. Let me just address that. I have to do this a lot. Actually, maybe this is faster. Much faster. It's a very good question. So, to get this result here, I have to assume this is called a non-uniform recovery. And that means that it says for a fixed signal with sparsity S, you draw a uniform at random, and the likelihood of being able to recover that now is greater than 1 minus epsilon. But it doesn't hold for all S sparse vector. It says for a fixed one. Now, uniform recovery with a rip says if I have a matrix that has the rip, then you will recover all S sparse vectors. So that is a stronger condition. And for that, you may have to pay. And I think the record now is it log 3 and then a log S? So there's essentially more log factors to be able to say something about the uniform recovery. Now for this rip in levels, since the rip is just a special case of that, if I could show that my matrix had the rip, yes, then you can do recovery. The question is, how many samples do you need? And it is conjecture that you actually only need S log n in that case, but that's not proven. And actually, if you do that, it will imply some famous conjecture of Bourgain. So it's a very substantial thing.
Thank you.
Other questions?
Be a silly question, but if you consider the non-uniform or even the uniform case, so you have your bound with your best error term plus the noise level and maybe a square root of S somewhere. I'm always a bit puzzled by this kind of result because the bound is not reduced when the number of measurements is increasing. So we will always pay the noise level.
Oh, you mean here?
No,
in
the stability and robustness
yes.
result.
Yes, let's go for that.
Yeah,
right,
you get only the stability here, but
yeah, I'll do the full one with the stability. Let me see. There we are. Yes. So you're absolutely right.
Yeah.
If I do full sampling, I don't lose the noise part.
Yeah.
I don't.
And
I won't.
Okay.
Because if you took an invertible matrix and I do the noise part, I will also get that in error. It may not be that bad as this, but you will still have a noise part. So
sure.
you reach the optimization problem here at the boundary. So the L1 optimization, where that will always get the minima or the candidate for which you apply that, and you're getting y plus the noise term. So it's an annoying thing, but you can never essentially get rid of the noise. Mm-hmm. But if it's noise free, you get rid of that part. Mm-hmm. Because then S is it could be anything. Yeah, that makes sense.
Is there last questions, maybe? Okay, let's thank Anders again. Thank you very much.
Thanks so much.